Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. Imagine you throw a ball straight up into the air, and then catch it at the exact same height that you released it at. At some point during the flight, the ball had to stop moving upward and start moving downward. Now in that split second, its velocity was exactly 0. This isn't just physics, it's Rolle's theorem. It guarantees that under specific conditions, a function must have a horizontal tangent line. Now before we dive in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. So let's take a look at Rolle's theorem. It states that if f is a function that satisfies these three hypotheses, then we can draw this conclusion. Now the three hypotheses are that f has to be continuous on the closed interval ab. Not only does it have to be continuous, it has to be differentiable on the open interval ab. And then lastly, f of a is equal to f of b. If all of these three conditions are satisfied, then we can conclude that there must exist a number c in the open interval ab such that f prime of c is equal to 0. So in other words, there must be a number that exists in the interval ab where the tangent line at that point is horizontal. Let's take a look at what that means through a diagram. So we're going to have our interval AB. So let's say A is here, B is here. Now f is continuous and differentiable on this interval, which means that when we draw our curve, we can't lift our pen up and it has to be smooth. And f of A has to be equal to f of B, so which means we're going to start at this height and end at this height. Now if the curve starts by going up, in order to actually get back down to our starting point, we have to come down, which means there's going to be a point here where the tangent line is horizontal. And similarly, if we decide to go downwards first, then at some point we would have to go back up. And where we change direction, that is going to be where our horizontal tangent line is. And of course, if we decide that we're not going to go up or go down, it's just going to be a horizontal line, then in which case, every point in between AB has a horizontal tangent line. Now we can take a look at how we can apply Rolle's theorem. For our first example, we want to verify Rolle's requirements for this function here on the interval 1, 4. So the first condition is that the function must be continuous. And since f of x is a polynomial, we know that polynomials are continuous everywhere. So therefore, this is continuous on the closed interval 1, 4. And then the second condition is that our function must be differentiable. And this is for the same reason. Because f of x is a polynomial and polynomials are differentiable everywhere, we can say that, therefore, this is differentiable on the open interval 1, 4. And from here on out, these two are going to be used as facts. Every time we see a polynomial, we know that it is continuous and differentiable everywhere. And the third condition we need to check is that f of a must be equal to f of b. So our a here is 1, and f of 1 is equal to 1 minus 5 plus 4, which is equal to 0. And f of b, so that'll be f of 4, this is going to be equal to 16 minus 20 plus 4, and this is also equal to 0. So which means we have f of 1 is equal to f of 4. So therefore, all three conditions of Rolle's theorem has been satisfied. So this means there exists a c in the interval 1, 4 such that f prime of c is equal to 0. And in fact, we can actually find that. So all we need to do is find the derivative of f prime of x is equal to 2x minus 5. And if we set that equal to 0 and solve for x, we get x is equal to 5 over 2. So our c value here is 5 over 2, and we can see that this is in the open interval 1, 4. We're going to take a look at one more example for another function. So here our function is 1 over x squared. And we're going to do the same thing. We need to make sure that all three conditions are satisfied. However, when we check our first condition, we can see that f of x is discontinuous at x is equal to 0. Because here we have x squared in the denominator, so if x is equal to 0, then we're going to be dividing by 0. And since the first condition is not satisfied, we cannot apply Rolle's theorem here. And now for our last exercise, we are going to prove Rolle's theorem. Now to prove this, we are going to split it up into three cases. The first case is if our function f of x is equal to some constant. So we're going to say f of x is equal to some constant, let's call that d. And if that's the case, f prime of x is going to be equal to 0. And this is going to be for all x in the interval ab. So this means we can pick c to be any value between ab, and f prime of c is going to be equal to 0. Now case 2 is going to be the case where our function f has a y value that is higher than our starting point. So that means we're going to let x be some value in between ab, be such that f of x is greater than f of a. But if that's the case, then this and the extreme value theorem is going to imply that there is a c value that is in the open interval ab such that f of c is the absolute maximum of our function f on the closed interval ab. Now, if f of c is the absolute maximum, then by Fermat's theorem, we have f prime of c is equal to 0. And now for the last case, we would have let x be in the open interval ab be such that f of x is now less than f of a. And similarly, as case 2, this and the extreme value theorem implies that there is a c which is within the open interval ab such that f of c is now the absolute minimum of f on the closed interval ab. And again, now we can use Fermat's theorem to say that since we have this local minimum in the interval ab and the function is differentiable there, we have f prime of c is equal to 0. And thus, we have proven Rolle's theorem. Because those three cases are exhaustive, a function f has to fall into one of those three cases. There isn't anything else. And now let's do a quick recap of what we covered in this video. We learned about Rolle's theorem in this video, and that there are three conditions. The first one being that the function has to be continuous, the second one being that it has to be differentiable, and the third one being that the endpoints have to have the same y value. And only when all three conditions are met, then we can apply Rolle's theorem. We'll also learn that if a function is a polynomial, it is automatically continuous and differentiable everywhere, and we're going to be using that as a fact from now on. And now it is your turn to give this a try. Can you find the solution to the problem on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.